here is our last topic for the waves unit. Now, what's going to happen is I'm going to give you 1 page of notes on this. We're going to do 1 page right now, reflection and refraction of light. The main point of this unit is going to actually be the biggest math part of waves, the most math that we will do, but we're going to do that in class on Wednesday together. Okay, we're going to practice that in class on Wednesday. But we're going to get this done first so that we can just kind of be caught up and so that we can get out everything finished for waves on Wednesday. Then after that, we just have a couple classes of notes on modern physics. We have 1 lab coming up actually on this topic right here, refraction. We'll do that on Thursday, I believe. And then we'll pretty much be good to go. Okay? So, yeah, I think we'll do it on Thursday. We'll see. Anyways, reflection and refraction of light. These are 2, and okay, I might just screw up the schedule. It's in the email that I sent you guys way back with the first videos. Just refer to that. I lost my train of thought for a second on what we were doing. Reflection and refraction of light. Last 2 things we got to talk about. We know that one way to show light moving from place to place is to draw successive wave fronts showing light moving in a certain direction. Okay? Wave fronts moving in a certain direction. There is an easier option. The easier option is to draw what is known as a ray of light. A ray is always drawn perpendicular to wave fronts, and it points in the direction the wave is traveling. Okay? Points in the direction the wave is traveling. So, for instance, let me give you some examples. Let's say you have some wave fronts like this. Okay, the wave is moving left to right. You would draw a ray like this. A little bit simpler to draw. If you had wave fronts like this, okay, let's say they're moving up and to the right, you draw the ray up and to the right. Let's say you had a point source of light that was, or anything really, that was emitting circular wave fronts of light. You could draw rays going in any number of directions as long as they remain perpendicular to the wave fronts. Okay? This shows light spreading out from a single point. Now, one of the things about light is that it is a transverse wave, but light moves in straight lines until it comes to a boundary between 2 different media. Okay, it moves in straight lines until it comes to the place where 2 different materials meet. And at that point, part of the ray will move into the medium, and another part will stay in the first medium. Okay? And this is what we're going to talk about with reflection and refraction. What happens when light goes to a boundary between 2 different materials? All right? That's the important part of today's lesson, this video. So erase this. Actually, you know what I'm going to do is I'm going to call the picture that we had been looking at previously. If you give me a second, I'll find it, hopefully. Okay, it's not in there. Did I save it under pictures somewhere? No, you know what? I probably didn't. Let's do this. Let's do... Maybe it will be here. Ah. I know what I can search. Well, I can't find the picture that I was using. That's kind of annoying. And I don't have any more time to look for it. So, what I'll do is I'll refer you back to one of the videos. I believe it was when we were first talking about waves, possibly intro to waves. We had a picture up there that showed some light. You know what? We'll just go without. Okay. Let me just show you this picture right here. This picture explains enough that we need. All right. So We have some light that is coming down onto the surface, and then you can see that the light gets split up. It goes in two different directions. Just like when we talked about waves being absorbed or reflected or transmitted when it comes to a boundary. Some of the ray goes in, some of the ray bounces back out. And all of these rays, these light rays, have specific names, okay? You have to know the names. The ray that approaches the boundary, we know it's this one because the arrow is going in towards the boundary. That is known as the incident ray. Okay? The ray that remains in the first medium, that one that bounces out, very obviously, okay, this one makes a lot of sense, is called the reflected ray. The ray that passes into the new medium is known as the refracted ray. So you have to be very careful because you have reflected and refracted, and they are different. They are not the same thing. You have to know whether you're talking about reflected ray or refracted ray. The word refract means to bend. Because if you notice, what happened here is this ray of light did not continue traveling in the same direction. It actually bent. Okay? It changed direction. All right? It changed direction. Now, we need to talk about the amount that something reflects, or the amount that something refracts, okay? Now, the reflected thing, I distinctly remember talking about this in like Mr. Noss's class in like 6th grade. So, knowing how much something reflects, and knowing is usually pretty easy. Knowing how much it refracts is where the math has to come in. Notice that since we want to talk about, what direction are all these rays traveling in, we measure their angles, okay? And notice that we're always measuring the angle between the ray and this dotted line here that says normal to surface. This line has a name. It is known as the normal line. Now, if you flash back to forces for a second, there was something in forces called the normal force. And a lot of you guys told me, oh, it just always points upward, but it doesn't. The normal force did not just always point upward. It pointed perpendicular to the surface that an object was resting on. The perpendicular thing is important. The normal line is a line that is perpendicular to the boundary between media. So here's the boundary, here's n, so don't worry about the n right now. This could be, let's say, air, this could be water. So this is the boundary between air and water, and the normal line is perpendicular to that. Okay, that's what the normal line is. You need to know what that is. You need to know what a normal line is. I shouldn't have to say it over and over again, okay? This is the normal line right here. All the angles are measured between the ray itself and the normal line. Notice there is no angle being measured here. They don't write this down. They don't write this down. They don't write this down. They are unimportant. You care about this right here, this angle, from the ray to the normal line. Please also notice, and this is the easy one to notice, just by inspection, you can look at these and you can see that what we would call the angle of incidence, or the incidence angle, you can call it either one, angle of incidence. How does it compare to the angle of reflection? Well, it is equal to it. It is equal to the angle of reflection. Another way to write this is, remember that's theta, that's a symbol for angle. Theta I equals theta. This is what the reference tables say. Because this stuff is in the reference tables. I believe it's page 5 for waves. I could be wrong on that, but let's take a look. I had a link up here for the reference tables, but of course I got rid of it because I forgot I needed it. Regions Physics reference table. Okay. And waves is page 5. Yes. Okay. So, on page 5, there's an equation right here that says theta I equals theta R. If you look at what those are, theta I is angle of incidence, theta R is angle of reflection, saying those two are equal to each other. Now, I'm going to modify that equation just a tiny bit because it annoys me that they put theta R, and however, there's reflection and refraction. So I'm going to do REFL for angle reflection. So there's no question about as to what you're talking about. The angle of incidence should always equal the angle of reflection for a light ray that bounces off at the boundary between some media. So some light will bounce off, okay? The amount of light that bounces off we don't have to worry about, but some light will bounce off, some light will transmit through and be refracted, okay? Now, the refracted ray, you can tell that it bends right here, Okay, it changes direction. It doesn't just keep going straight, it bends. And the reason that it bends, I believe I can fit this without scrolling down. The reason it bends is due to the fact that these are different materials, okay, different media. So what happens? Light will change its speed. The speed of light is different in different media. Okay? It's different in different media than it is in a vacuum. If a wave approaches a boundary at an angle, the reason that it bends has to do, you got to think back to when we were talking about wave fronts, okay? There's a picture down below that can help a little bit with it. So you know what? I will erase and go down so we can refer to the picture at the same time. So the reason that this happens is because refracted ray bends due to the fact that the speed of light is different in different media than in a vacuum. So if a wavefront approaches a boundary at an angle. Okay, so we've got a picture here that depicts both rays and wavefronts. So the ray comes in at an angle. That means the wavefronts are also, they're perpendicular to the ray, but they're also coming in at an angle. And look what happens. Part of that wavefront is going to go into the new material before the other part. Okay, the left-hand portion of this is going to go in before the right-hand portion of the wavefront does. Remember, this is all light. It's not just one little beam of light. It's light coming in at an angle. It's a whole bunch of light. So what happens is, in order to keep drawing the wavefronts, well, if this part of the light, when it enters a new medium, slows down, then the wavefront is going to change direction. Because all of these all this light right here has slowed down. It hasn't traveled quite as far now. And what this ends up doing is it ends up turning all of these wavefronts. The light actually physically changes direction because what we're trying to show here is, again, with the wavefronts, these are all points that are in phase. Because some of those points are slowing down here, the line has to turn so that we can draw a line through all the points that are still in phase with each other. And this doesn't just work for light waves, it also works for sound waves. It actually works for water waves too. There's some really interesting applications of this idea that when you go from one medium to the next, speeds decrease. So anyways, part of the wavefront enters the new media before other parts. This makes that part of the wavefront slow down before the other parts. Since the wavefront consists of all points that are in phase, what if we still try and draw the wavefronts, showing which ones are in phase, it's going to start to change direction right there because these points have slowed down a little bit. They're not moving fast enough anymore to be out here, okay? They have slowed down a little bit, and this wavefront has kind of got a little kink in it. And as more and more of the light enters the new medium, it will change so that more and more is at this this kind of angle. Then when it's all in, now the wavefront itself has completely changed direction, which means the light ray that we draw perpendicular to it has also changed direction. This means light has bent. Okay, the light has bent when it's gone into the new medium. You guys are used to seeing this, okay? In class, I can show nice demonstrations of this with lasers, and we can see them actually bend. You'll do a nice lab on this in class. But this is something that happens if you put a pen in a glass of water, or a pen or a spoon or something like that. You look at it and you're like, oh, it looks broken or it looks bent. That is refraction. That's the refraction of light doing that. It's not actually bent or broken, but that is why it is happening. Okay, so we go to the back. I'm going to try and do this all in one video this time, so it might be a little bit on the longer side. When we talk about light, so I'm glad I still have this up. I want you to go to page 2. We talked about electromagnetic spectrum last time. Now we're going to talk about this bottom table. So really, if you think about it, we got 1.5 pages left to go on the reference tables. That's pretty good. Okay, so here's that table. It should say absolute indices of refraction. I'll explain what that means in a little bit. It has to do with the idea that light travels at different speeds through each of these different materials. Okay? And the reason it travels at different speeds is roughly according to the density of the media, of the material. It's not exactly proportional to the density, but for our purposes, it's close enough. Okay? It's about the density. The speed decreases for denser material because the wavelength will actually decrease for denser material. I guess it's really the other way around. I guess the wavelength decreases because the speed decreases. Really the way I've always thought about it, whether it's perfectly right or not, I'm not really sure. But if you have a denser material, the light kind of bounces around between all these different particles. If you have a very not dense material, the light doesn't have to hit very many of them. If you have a denser material, the light's path gets slowed down as it gets, interacts with all these different particles, molecules, atoms on its way through. It takes a much longer time for it to propagate through a dense material. But anyways, the point is, in a denser material, the speed decreases and the wavelength decreases. Okay? For a single light wave moving between media, the frequency does not change. The frequency will remain the same. It is just the speed and the wavelength that decrease. Okay? So if you've got one light ray going from one material to the next material, the frequency will stay the same. The velocity and the wavelength are what will change. We can actually quantify how much a medium will slow down light by calculating what is known as the absolute index of refraction. Okay? The absolute index of refraction. Here are a whole bunch of plural is indices of refraction. Okay? You have air, cornoil, diamond, blah, 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 all the way down. Got a really high one right here in diamond, okay? Next highest, I believe, is zircon. And then a lot of them are in like the 1.3 to 1.4 range. Air, notice, is just 1, okay? And it does say this is for frequency, for these specific frequencies, because they do change based on the frequency, but we're not that advanced. We're not going to talk about that. In general, these are what you need to know, okay? Absolute indices of refraction. All right? A higher value means that the medium slows down light more. So, diamond, really high index of refraction, slows down light a lot. Water, not a very high index of refraction, slows it down, but not as much as a lot of these other ones. The equation for index of refraction is on page 5, under waves. We're going to do all of our waves equations today, or at least we'll write all of them. Right here, index of refraction symbol is N. N is equal to C, which is the speed of light in a vacuum, divided by V, the actual speed or velocity. And what that means, this equation, okay, so N is the index of refraction, C over V. C is the speed of light in a vacuum. V is the actual speed of light in some material. And so basically what we do is we take the speed of light, we divide it by what the speed of light actually is in a particular material, like water or diamond or corn oil or glass or whatever. And when we divide these two, whatever comes out is the index of refraction, this N. The important thing for this is that there are no units. All N is, it is a constant for a particular material, and it's different for every material. So it's a constant that varies for each material. We'll do 2 examples to give you the right idea. What is the index of refraction for a material in which light has a speed of 2.4 times 10 to the 8th meters per second? We're going to use our equation, N equals C over V. We know that C, speed of light in a vacuum, is 3 times 10 to the 8th meters per second. The speed in this material is 2.4 times 10 to the 8th meters per second. We divide these two. We end up with the index of refraction is approximately 1.25. That is what defines how fast light travels in this material. Okay, 1.25. This is the actual speed, but it's just easier to talk about it if we talk about N. Okay. Now, this does not have to match with something on the table. It can be whatever value you want. Typically, you're not going to have below 1, because if it was below 1, that would mean V is bigger than C. That can't happen. And you don't really ever see anything above diamond either. So if you get some really big number, you're probably wrong. Okay? But anyways, this is what would define the material. Okay? 1.25 is the index of refraction. We can go the other way with this too. What is the speed of light in sodium chloride? Well, I know that sodium chloride has an absolute index of refraction of 1.54. So I write my equation, n equals c over v. I plug in 1.54 equals 3 times 10 to the 8th meters per second divided by v. And I solve for v, and based on my index of refraction and based on the speed of light in a vacuum, I can calculate that the speed in the sodium chloride is approximately 1.95 times 10 to the 8th meters per second. That is the speed in sodium chloride. So, again, the reason we calculate indices of refraction is so we don't have to just talk about their speeds. So we got a nice, quick, easy way to see, okay, well this is pretty dense, this is not quite as dense, using lower numbers that are just a little easier for us to understand. This is not how fast something is moving, this is just the index of refraction, it's just a number, okay? V is how fast it moves in the material. Alright, so, this equation, n equals c over v, actually turns out to be pretty useful. What I'm going to do for the next few minutes is kind of show you some manipulations of that equation that lead to some nice consequences, okay? That lead us to some other equations. We started with n equals c over v, but you know what? We could rearrange that equation to solve for c. We do that by multiplying both sides by v, and we should end up with this. C equals n over v. Now, c is a constant, remember. So c cannot change. Speed of light in a vacuum is defined. It is a constant, it does not change. N and v, therefore, if n goes up, v must go down, so that it's still equal to c, the product. If n goes down, v must go up. These two are inversely related. They're inversely proportional to one another. C is a constant. It's the speed of light in a vacuum. And since it's a constant, we could say, well, since c will never change, any product of n times v should always equal c. So we could write that n1, v1 should equal n2, v2. If you know the index of refraction and if you know the speed in a certain material, that should be equal to the product of the index of refraction and the speed in a different material. And I'm kind of going through some derivations right now. I'm not expecting you to understand and to be thinking, oh yes, that's obvious we could do that. I just need you to follow along and see where we end up. We can rearrange this if we get all the n's on one side, all the v's on the other. I could rearrange this into n2 over n1 if I divide both sides by n1. And then I divide v2 over to the other side. I see that n2 over n1 should equal v1 over v2. All right? So this shows us that, well, it doesn't really show us a ton right now. I'll wait on that for a second. But one more thing that I want you to recall. We also know that for waves, the speed of a wave must be equal to the frequency multiplied by the wavelength. So we can write this. n2 over n1 does equal v1 over v2, but any speed is equal to the frequency times the wavelength. The reason that I'm going so in depth with this is because, remember, if we have two different media, a light wave can travel between those two media. So we can take something from the first medium, put it into the second medium, the speed should change. What shouldn't change, however, remember, is the frequency. It should be the speed and the wavelength that change. So if we have a light wave going from one material to the next, the frequency should be the same for both materials. The wavelength should be different. What can I do with these f's right here? I got one on top, one on the bottom. I cancel them out. I'm left with this relationship that shows up in your reference tables. n2 over n1 equals v1 over v2, which is equal to lambda 1 over lambda 2. The reason that we're doing this, let me show you that this is in the reference tables really quick. The reason that I'm showing you all of this is simply because it is right here in the reference tables. It's the last equation down in the wave section, okay? Do you ever have to actually, is your life ever going to depend on using this? Okay? Not life, but is a question going to depend on you using exactly this? No. This is just a quick, easy way to see how the index is related to things like the speed and the wavelength. Okay? You don't have to actually use this. It's useful sometimes, and it saves you some trouble, Because otherwise you have to use this like a whole bunch of times, you got to use this equation a whole bunch of times, but it's never going to be an expectation that you use this. But it saves you some time, okay? This is the full relationship of, the full picture of the relationship between the index of refraction of a medium, the speed of light in a medium, as well as the wavelength of light in a medium. Okay, this set of equations shows the relationship between all of those. Our last topic is Snell's law. Okay, the reason we got to talk about Snell's law, which is the last equation in your reference tables for the in the waves section. Okay, that is Snell's law, so you can actually go ahead and write that down here. Is because we said already that we know that the angle of incidence is equal to the angle of reflection. Well, there's actually a way to predict what this angle should be as well, the angle between the normal line and the refracted ray. And in order to figure that out, we need to know not only what the two materials are, but also what the angle of incidence is. And if we have all that, we can predict the angle of refraction. And that is that equation, that relationship is given by something called Snell's law, which is right here. Okay? So that is where we will stop for today, as soon as we get a couple of things written down. In order to determine the angle of refracted light, once it has crossed the boundary, we use Snell's law. I wish I was Snell. I wish I had an equation named after me. Snell's law is, as the reference tables told us, N1 sine theta 1 equals N2 sine theta 2. Typically, the left-hand side will be for the incident ray. The right-hand side will be for the refracted ray. And just a note, since we do have thetas in here, please, your calculator, there's no reason for your calculator to be in anything but degrees in this class. Calculator must be in degrees. It has to be. There is no reason for it to be in radians in this class ever. So you need to change your calculator. If it's in radians for pre-calc or calculus, you need to change it to degrees. That's all I want to talk about for reflection and refraction of light. We'll pick up with the rest of that later on. Thank you.